Hello, my friends. How you doing? Welcome to this quick review on Little's Law. It's a topic that's come up several times in our preparation for the PMP exam, so I decided to address it once and for all with those of you who are curious to know a little bit about it. The basic concept of Little's Law reinforces the idea of reducing something called your work in progress, also known as WIP. Little's Law basically states the more work you have in progress, the slower you are, and the longer it takes to get work done. Little's Law is a law, it's not a theory, and it's behind some of the math in queuing theory. One thing to consider is if you want to increase throughput meaning producing more things, then limit your work in progress. Let's take a look very quickly at the overarching theories, and then we'll go into some examples and I'll ask you a few questions. So here's the overarching theory. The long-term average number of customers in a stable system, let's call this L, is equal to the long-term average effective arrival rate, which we will call lambda, multiplied by the average time a customer spends in the system. Let's call that W, or wait time. So when we take a look at these parameters, L is the average number of items, known as WIP, in a queuing system. Lambda, the average number of items arriving at the system per unit of time. We call it throughput. And W is the average waiting time an item spends in a queuing system. We also refer to this as lead time. Now, taking a look at this equation, there are so many parameters. First of all, you've got the strange looking lambda, and then you've got letters on the left that mean something totally different when you try to reconcile an L and a W, or a lambda and a T for throughput, or a W and lead time. So I want to share with you my unique way of viewing these parameters such that you will never forget what they mean. Okay, so this is the trick to remembering Little's Law, where you have an L for work in progress, you have a W on the other side. So you've got something like this. You got an L, and that really means work in progress. You got lambda, and that really means arrival rate. But don't forget that when we say arrival rate, we actually mean throughput. You see why it's so complicated to remember this formula? Because you got letters fighting all over the place. It's a very simple formula, but you just need to remember what is what. And last but not least, we've got a W again on the left, which does not mean work in progress. Instead, this W means lead time, also called wait time. Okay, now let's go to the whiteboard and make even more sense out of this. Okay, on this whiteboard, I want you to think about it like this. Little's Law, okay? You got to remember that the arrival rate is written as lambda. So when I think of lambda, I think of an A. That's the way I get around it. And I think of arrival rate, okay? The W I think of wait time. See? A for arrival, W for wait, and L really means in line. Waiting in line. Get it? Work in progress. Wait in line. So when you boil it down, you have the work in progress is equal to the throughput times what we'll refer to here as lead time. So whether you think about it in terms of L is equal to lambda times W, or you think about it like WIP is equal to throughput times lead time, you're going to have a much more robust understanding when you can think in these parallel lines. So, law and whittle sounds like little. That's it. That's simple. Law and whittle. Whittle sounds like little. WTL sounds like little, okay? Just remember, work in progress, throughput, and lead time. That is exactly what this stands for, what this stands for, and what that L stands for. One layer of understanding on top of this, think about this as meaning in line, waiting in line, work in progress, okay? Think about the A as arrival time or arrival rate, I beg your pardon. It's a rate, that's throughput, arrival rate. And lastly, wait time. If you think about it like this, it's going to be easier for you to remember all the parameters because, to be quite honest, they're swimming all over the place. You got to keep them straight. All right, let's go back to our PowerPoint. So, one more time. L is equal to lambda times W, where L is WIP, lambda is throughput, and the W, wait time, known as lead time. So lead time is the total time spent in the system, whether you're working it or not. The moment it's in the system, you begin to count lead time. Now, there's a difference between lead time and cycle time. Lead time is all the time that item is in the system. Cycle time, which you hear in other circles, is the amount of time that item is being worked on. So we think of lead time from the customer's perspective and cycle time from the performing organization's perspective. Just keep that in mind. So this formula could be written in a number of ways. And if we choose to write it as L equals lambda times W, we could also say that lambda is equal to L divided by W, or W is equal to lambda divided by W is equal to L divided by lambda. However you want to spin them around. If we decide to write it as WIP equals throughput times lead time, then we can manipulate it to look like this. WIP divided by throughput equals lead time, or WIP divided by lead time equals throughput, so on and so forth. All right, so if you want to increase throughput, then limit your work in progress. If you want to speed up the process, that is reduce lead time, then limit your WIP. It is all about work in progress. That's the bottom line. So once you wrap your mind around this, you'll be able to answer trivial questions such as this. Your team wants to measure the cycle time within the current iteration. The mathematical principle they should use is what? Now, remember, I told you there's a difference when we talk about lead time and cycle time. However, you can extrapolate what the cycle time is when you have the right parameters. But taking a look at the options here, it becomes very, very obvious that what they are looking for is one and only one option. Okay. So when we look at the options we've got, the answer we should select is, and the answer to this is C. Now you will see this calculation written in a number of ways, but in the interest of your exam, when you hear them asking questions around cycle time, lead time, you know they're pretty much referring to the principle called Little's Law. All right, so the answer to this is C. Let's take a look at another example. You own a small store that makes donuts for neighborhood kids. On average, 40 kids are seated in the facility, eating and playing with friends. They usually stay for 20 minutes before leaving. How many students come through every hour? So, what they're asking for in this question, you should be able to work out, and you should arrive at the correct answer using the formula in Little's Law. All right, so why don't you go ahead, play with this for a few seconds, hit the pause button, and then check the answer I'm going to share with you. All right, 3, 2, and 1. Okay. So to work this problem, my friends, right off the bat, you want to put labels on some of these things so that you know what is what. So it says, on average, 40 kids are seated in the facility eating and playing with friends. That means that is in progress. So you're going to say L is equal to 40. And next it says they usually stay for 20 minutes before leaving. And then it says how many students come through every hour. So your unit of measure needs to be hour. You need to convert this 20 minutes into hours. So this 20 minutes, we're going to refer to this as our wait time. We could also refer to this as our lead time, if you will. So wait time, lead time. In other words, how much time is spent working on these things. Okay, so they spend 20 minutes. Think about that 20 minutes as the wait time or the lead time. So I'm going to say the wait time is 20 minutes, which is equal to 0.3 hours. Why 0.3? Because 20 divided by 60, actually 0.33 hours. 0.33333. All right, so that's the idea. You got to convert to the right unit. When you got this, the next step is to substitute them in the formula. Now remember the formula is L is equal to throughput times wait time. We're going to switch this around to show throughput is equal to work in progress divided by wait time. Okay, or W rather. So if you do that, you will arrive at 121.21 roughly. So the correct answer for this is A. Again, to solve it, you need to put the right labels on and you need to make the right conversion. Okay? Let's take a look at yet another problem to better help understand this. This states you own a manufacturing firm where the throughput is 4 statues per hour. The lead time is 10 hours. What is the WIP in this system? Well, remember the formula is whittle where T is throughput and L is lead time. And of course, W is WIP. Or remember, it's the law, right? L is equal to A, arrival rate, or lambda times W, however you want to look at it, okay? Don't forget, when I use an A, it's really the same as lambda, but I'm just giving you a way of coping with remembering it since it looks like an A. All right, so if we substitute in here, the WIP is equal to the throughput of 4 per hour times the lead time, and that's 10. It's already in hours. So the WIP in this case is 40. And the answer to this question is just that, 40. Okay? The more you look at these problems, the easier it's going to get. All right. So one more small definition to get you more into it. Remember whittle, WTL, W equals T times L. Well, L, lead time in this case, or wait time, is how much time the job is in the system. Like I said in the beginning, throughput rate can be considered average completion rate. WIP is work in progress, and that's how you solve it. It's that simple. Now, what happens if you want to increase the number of units being worked on? In other words, you want to increase your work in progress. You want to do more work. What will the impact be on the system? Well, because you can only get 20 done, because you can only get 4 done in an hour, you will only end up getting 20 done if you put more work in progress. So instead of 40 units, let's say you wanted to work 80 units because you think you're being more productive and you put 80 units into that system, well, you can only get 4 units done per hour. So it's only going to double your time. Putting more WIP into the system is only going to double your time. So let's take a look at that. If you say, I want to work 80 units, I want to get more done. Well, you can only get 4 done per hour. Your throughput rate still the same. And therefore, the lead time will increase and thereby extend the amount of time before one of those items can get to your customer, which is not good. Not good. All right. So I hope this is helping you with your understanding. I'm going to show you a few more problems. Here's another problem. As an Agile practitioner on a 4-week iteration, you've determined that there are excessive bottlenecks occurring. You're very concerned about issues with throughput. What would be the best course of action to take to address this issue? I'm going to give you a minute to think about it. All right, my friends. So now you can see the best thing to do is, of course, to limit work in progress. That we have seen to be true. Limit your WIP if you want to get rid of these problems, okay? Excessive bottlenecks, definitely an indication that you got too much WIP. Let's go to our next question. You're an Agile practitioner and have noticed that several team members are often sitting idle and are not productive. What most likely accounts for this form of waste, and how can you best resolve the issue? Again, I'm going to give you a minute. All right, 3, 2, and 1. Okay. So if you have a system and the components of that system are not engaged, it means most likely there's no work in progress. In other words, work is already done. So they are idle. An idle machine just means there is no work to engage that machine or that individual, that resource. So what most likely accounts for this form of waste is that your work in progress limits may be set too low. If your work in progress limits were not low, those resources would be engaged. All right, here's another question. You're the owner of a small hot dog stand. The hot dog stand is parked at a school district with minimum seating. Every day, students visit the hot dog stand. On average, 10 students stay in the premises, eating their hot dogs and having drinks for 30 minutes before leaving. How many students come through every hour? I'm going to give you a minute. Think about it. All right, well, I hope you had fun working on that one. Let's take a look at the answer. So you got to put some labels on these things. 10 students stay in the premises eating their hot dogs and having drinks. That should immediately tell you that the WIP, also known as L, okay, is equal to 10. And then it says having drinks for 30 minutes before leaving. And that number 30, we need to convert it into hours because it said how many students come through every hour. So if we convert 30 minutes into an hour, into hours, we get half an hour. So that means our wait time is equal to 0.5. right? It's 30 minutes, but 30 minutes is half an hour. So what we're going to do is put these into the equation, and we're going to have, remember, it's either whittle or it's law. Okay? So if we use L being the work in progress, A being the arrival rate, which is what we're looking for, and W, the wait time, then we can say lambda is equal to WIP divided by the wait time. Okay? And that will give us 10 divided by 0.5, and that's equal to 20. And that's why the answer is A, 20. All right, I've got just a couple more. Let's go to our next one. Phil works at Praizion, a PMP training system where students receive rapid hybrid training to become PMP certified. Every week, there are 6 new PMP certified. At any point in time, there are 3 students in the PMP system receiving hybrid conditioning for their certification. What is the lead time for this system? So I want you to visualize for this one. Let's give you a visual. Think about this as a system. And it said, at any point in time, there are 3 students. 1, 2, 3. 3 students in the system. Okay? And then it gives you a unit of a week. So you need to be thinking in weeks. Okay? But every week there are 6 new PMP certified. So again, another visual, 6. 1, 2, 3, 4, 5, 6. So you have your work in progress. That is how many we have in the system at any point in time. Okay. We have the throughput. You want to call it arrival rate. Some people also will refer to this as departure rate, just so you know. You might hear that term again, departure rate, okay? And then the last parameter that we have is the lead time. And that is what the big question mark is. Okay, the lead time. But it's a very simple calculation if you use the whittle acronym. Okay, using the whittle acronym, it is very easy to see what this relationship is. And I'm really hoping that it helps you the same way it helped me to visualize it. Okay. That is a visualization of what is really happening. See, you can visualize your W, your WIP, your T, the throughput, call it arrival rate or departure rate, and then the lead time. Now, when we talk about the lead time, one more thing I would like you to visualize. This lead time is really referring to the items. How long would one of these items stay in this system? Get it? Okay. So with that in mind, you should be able to solve this problem. We are going to substitute for the WIP, which is 3. So think about the WIP is 3, okay, obviously. Think about the throughput. Now the throughput, we're going to put this into weeks. But remember, in a week, we have 7 days. So it's 6 per week, or 6 every 7 days. With that in mind, we could actually make this conversion when we get towards the end of the problem to convert our week, remember, week into days. So if we're getting 6 done per week, it means we're getting 6 done every 7 days. So when you take this calculation and you convert it as follows, you're going to have WIP equals T times L, which means the lead time is equal to the WIP divided by throughput. Get it? And when you do that, you're going to get 3 divided by 6, which is 0.5. Remember, this is in weeks, okay? Now, you have 0.5 weeks. What is a week? 7 days. Multiply 0.5 times 7, and you get the answer of 3.5. Okay, does that make sense? So let's get rid of all of this on the screen and let's show the very simple way of looking at this. A simple solution is WIP divided by throughput, 3 divided by 6 per week, 0.5, and the answer is 3.5 days. In other words, these students will be in the system for 3.5 days. All right. Well, I believe that's it. That's all I've got as far as Little's Law is concerned. So let's wrap this up and end this episode. Okay. So if you want to increase throughput meaning producing more things, then limit your work in progress. If you want to speed up your process, taking less time to produce things, limit your work in progress. Regardless what you want to do. To paraphrase, if you want to make things faster, if you want to produce more stuff, reduce your work in progress. Okay? I know that this flies in the face of all that we've been taught for many years. It's always been about individual achievement, being busy, but it's not about being busy, it's about getting stuff done. So instead of focusing on starting a whole bunch of things, instead, reduce the work in progress, look to the right. If you're using a Kanban board, get stuff finished. Okay? Stop starting and start finishing. This can't be emphasized enough as to how core and critical this is to efficiency of an organization. Focus on limiting your work in progress, reduce the number of projects you're working on, and reduce the number of things you're doing together as a team and get it smaller. Reduce the amount of work in progress, and you'll be amazed at the efficiency gains. You'll get things done faster, and done is important. Starting is not. and that's our goal. Okay. I would advise you to go look up some of this information on Wikipedia. They have an extensive page on Little's Law. The more you look at it, the more it's going to stick. Remember LAW, law, remember WTL, whittle. Whittle rhymes with little. I hope this helps you. Thank you very much for joining me, and talk to you soon.